Wait. Before we dive into today's topic, let's see two key questions that were left unanswered last week. Questions that will help us better understand the deeper issues behind the project delays. TBM is used in straight tunnel sections, while SEL is used in curved or complex areas. But how can such large construction methods be switched in narrow underground spaces? TBMs are typically built to lengths of 16 to 100 meters and in special cases even over 120 meters. As the length suggests, TBMs are specialized for straight sections capable of excavating long, uninterrupted paths in a single drive. However, this strength becomes a limitation in highly curved sections. Navigating tight bends with such a long machine is no easy task. In these areas, spray concrete lining SEL is required, as it is better suited for curved tunnel construction. It uses smaller, more flexible equipment that can be maneuvered more easily. To transition from TBM to SEL, the TBM must be disassembled at a shaft or chamber. Thanks to its modular design, the TBM can be extended or reduced relatively freely to suit the conditions. Based on the previous question, what we need to focus on is how to disassemble the TBM and introduce SEL. First, the TBM is disassembled and pulled up to the surface through a shaft or chamber. Then, SEL equipment is brought into the same space. Since SEL is relatively small, it can easily be introduced. Once inside, the SEL method is used to complete the excavation of the curved section. After that, the SEL is removed and brought back to the shaft or chamber, where the TBM is reassembled and continues its work. However, if the process of disassembling and removing the TBM is not feasible or efficient, an alternative method is to permanently embed the TBM underground. This is particularly used in urban areas where the space is limited. In such cases, the TBM is permanently embedded at the end of the tunnel, a process known as a TBM abandonment or the sacrificial TBM method. The embedded TBM is fixed and sealed by filling the space between the body and the exterior with concrete, turning it into a closed-off area. As a result, it becomes part of the tunnel's end, completely isolated from the outside, making it inaccessible to trains or people. In fact, at Paddington Station, the steel cylindrical structure known as the shield, which is difficult to move, was buried in the ground. Parts of the TBM that were modular and easier to disassemble and remove were separated and taken out. Another exception is that TBMs, while specialized for straight sections, are not completely incapable of passing through curved sections. The ability of a TBM to navigate a curve depends on the radius of the curve and the size of the TBM. While TBMs are equipped with mechanisms that allow the machine to rotate in the direction of the curve, they can only pass through the curves with a minimum radius of 150 to 200 meters. In cases of tighter radii, it becomes difficult for the machine to change direction. In the case of London's Crossrail project, some TBMs were able to pass through the curved sections as a minimum radius of 200 meters was available, allowing the work to proceed. After the TBM reaches a station in the shape of a concrete box, one method is used to move the TBM to the opposite tunnel across the station. In the process of tunnel boring, there are cases where the station box is constructed first, and other cases where the ticket hall is built after tunneling. Canary Wharf Station falls under the category where the station box was constructed first and the TBM passed through the afterward. So, TBM had to travel about 260 meters inside the station. In this case, there was a height difference between the station box and the station floor, and to overcome this, a lifting bracket was used. The lifting bracket is a horizontal sliding support system that assists the crane in moving the TBM. It lifts the TBM body and helps it move to the next position. It also distributes the weight of the TBM efficiently, ensuring that the TBM load is not directly transferred to the station structure. Let's dive into this week's topic, the complex process of managing a project involving multiple fields. The construction of the Elizabeth Line involves not only many incidents and delays, but also carries significant historical value. As this line stretches across cities from east to west, the process of digging beneath the surface also revealed the parts of each city's past. In total, over 40 significant archaeological discoveries were made. In West London, prehistoric settlements were uncovered, and near the Farringdon station in East London, the remains of 25 victims of the Black Death were found. These are remnants of a darker past discovered by engineers digging tunnels next to Charterhouse, a Tudor-style mansion built on the site of a 14th century monastery. At Liverpool Street, remnants of the city's defensive walls and various roads from a London settlement that housed around 60,000 citizens over 2,000 years ago were uncovered. These human remains, discovered during the construction process, are invaluable assets to the local and national history, and as such, required further investigation by archaeologists. In some cases, this investigation took up 22 weeks, causing unavoidable delays. This highlights how the process of building a structure is not just about architectural engineering, but also about the collaboration of many different experts in related fields. Next, let's discuss the area of contracts. The construction of the Elizabeth Line, like any large-scale project, involved a complex contract structure with numerous stakeholders, creating a multi-contract environment. This brings us to the third issue. The Crossrail project was made up of 63 major contracts, each closely interconnected. Due to coordination issues between interfaces and unexpected site conditions, there was a high likelihood of delays. As a large-scale project, the construction was divided into various categories, such as tunneling, station construction, system installation, and general civil works. Notable contracts included C300, C305 for tunneling, C430 and C435 for station construction, and C610 for system installation. During the construction process, tunneling had to be completed before station construction could begin. However, delays in tunneling pushed back the station construction schedule as well. Additionally, different contractors were involved in each contract, making coordination between works challenging. Inefficient communication ultimately led to further delays. For example, at Farringdon Station, tunneling and station construction were carried out simultaneously, but the lack of sufficient communication and coordination led to unexpected issues. The delay in completing the Western Tunnel prevented the delivery of materials and equipment for the station construction. Since both the tunneling and station construction equipment had to use the same access route, the overlapping work schedules caused inefficiencies. And also, the Farringdon area itself was narrow and complex, limiting the space available for equipment placement and material movement. The original design required the full 500-meter platform tunnel to be constructed before the TBM's arrival. This posed the risk of delaying TBM excavation and required relocating the machine using lifting brackets or similar equipment to the next drive. Instead, the contractor BFK proposed an alternative approach to first excavate a pilot tunnel using the TBM and then widen it into a full platform tunnel. This ensured that the two operations did not interfere with each other, allowing the project to proceed smoothly. Meanwhile, another unexpected situation occurred at the Thames Tunnel. This tunnel, which passes under the River Thames, faced unexpectedly high water pressure, causing excavation work to halt. The initial groundwater level predictions were inaccurate, leading to water seeping into the tunnel, which made it impossible to carry out waterproofing work. These locations were all situated within weather chalk layers, characterized by heterogeneous ground conditions, including numerous orthogonal joints and flints. Due to these conditions, it was not feasible to perform waterproofing operations in parallel with the TBM excavation. Therefore, ground pre-treatment was required prior to full-scale excavation. To block groundwater inflow and ensure excavation stability, the Crossrail team employed tube unmanched grouting methods, using microfin cement around the crust passage areas. Additionally, due to the low strength of the upper chuck layer, grouted glass reinforcement plastic dowels were installed to further reinforce the ground. As a result of the grouting, the permeability coefficient of the ground was reduced below the target level, and groundwater inflow was effectively blocked in most sections. This issue also impacted the installation of the power systems, which could only proceed once the tunnels in tunnel walls were completed. With delays in the waterproofing work, the power system installation was similarly delayed. Particularly, the suspension of track and power wiring work caused delays in the subsequent signal system installation. Of course, the installation process itself also had difficulties, further complicating the timeline. The Elizabeth line had to integrate 3 different signaling systems: ETCS, CPTC, and TPWS. Compatibility issues between the CPTS and ETCS led to errors between the train software and signaling systems, causing significant delays in resolving these problems. To address these, CPTC, which is used for urban areas, was integrated first to ensure stable operation in the central underground sections. ETCS, the high-speed signaling system, was prioritized later and gradually stabilized after the line opened. To prevent issues where trains might stop due to problems with signaling switching, a reset function was introduced, allowing operators to quickly restore the system through manual intervention. The final consolidation category is finance. Finance is the key pillar that holds the beginning and end of construction. As much as the process stops when the flow of money stops, it's a critical issue that determines the overall project. The Crossrail project utilized a public-private partnership model, where public and private entities collaborated to secure funding and facilitate the construction of certain sections of the project for the public benefit. Some sections were built through direct investment by real estate developers and private companies. A prime example is the Canary Wharf Group, which contributed £150 million towards the station's construction. In return, they developed commercial space and a park above the station, generating rental income. This included 100,000 square feet of commercial space and rights to a rooftop park. It was a typical PPP model where a private company built public infrastructure while also generating revenue through commercial space. Particularly, private investment was encouraged around station areas where development purposes were clear, aiming to create a win-win situation by offering private companies opportunities to generate income. However, due to the nature of public transport infrastructure projects and the lack of a clear mechanism for directly recouping profits, this approach did not yield the expected results. As a result, the majority of the construction costs were borne by public institutions such as the Department for Transport and Transport for London. As a large-scale project, there are so many different fields. Complexity, issues, and delays were proportional. With so many issues and long delays, the construction of the Elizabeth line, including the completion of our station at Canary Wharf, inevitably led to significant financial losses. The initial construction cost of £14.7 billion ballooned to £17.6 billion and ultimately reached a staggering £18.8 billion. After all, process management is not just a matter of time, but also a matter of cost directly. In a world where one-day delays cost hundreds of millions of won, contractors cannot relax for a single day. This week, we covered issues related to contracts during construction, delays in the integration of the signaling system, and the resulting cost problems across the Crossrail project. Next week, we will focus on the construction process of Canary Wharf Station, discussing the construction of cofferdam built over water and how it differs from typical station construction. In weeks 8 to 9, we will cover the construction methods used after the cofferdam, including the building of the roof garden and the structure and materials of the roof. Finally, in weeks 10 to 11, we will conclude the presentation by telling the overall story of our building.